But in my case, so no apology for that. But in my case, this goes a little bit further than that, because it is really on the border with, say, four-manifold topology. And so the topic is essentially algebraic geometry, especially of K3 surfaces, at the surface of a four-manifold. And to be a bit more specific, it is something like that you could call a Thursdonian program for the K3 manifold. Now, my collaborator is Benson Farb, who is indeed a former student of Thurston. And by the Thursdonian program, he means the following. So for this I have to recall a little bit about what Thurston did in the 1970s. It was really a breakthrough type of work, and that regarded the classification of mapping classes of a surface, or topological surface oriented, so something closed, a certain genus. Better assume the genus is at least two. If you have so here's the surface, and if you have a mapping class, so a mapping class is the same thing as just an isotopic class of diffeomorphisms, perhaps in this case better take homeomorphisms. Then, so let's take an element in here. Then there's an asserts that you can decompose this surface into pieces in a way that is quite similar to what you find if you have a Galilei-Mumford stable degeneration of a curve. So these then would be the vanishing cycles, right? Something like this. Well, such a mapping class will preserve the isotopic classes of these curves. At least that's the way you choose them. You choose them maximal for that property. And then a power of phi will, of course, have the property that it preserves every connected component of the complement. And then Thurston asserts that we can choose this phi, a representative of phi, so we can actually a phi tilde. So it would be orientation preserving diffeomorphism with the property that the power will preserve every connected component and acts in such a connected component either as the identity or in the most complicated way possible, namely as what's called the Tsuno-Hausdorff diffeo. And that means basically that you have in such a connected component, you have two transversal foliations like this, a little bit more than foliations. They're given by zero sets of one forms, closed one forms, and the phi tilde then preserves that foliation, each of these two foliations, and acts on one of the one forms as a multiplication with a scalar greater than one, and on the other one with the inverse of that scalar, so smaller than one. And that's a rather deep result. And it's a little bit, at least people compare it with the classification of a linear transformation, say, of a complex vector space. If you have such a transformation, you first of all can, of course, write it as something that is composite of its unipotent part and its semi-simple part. And if you then raise it to a suitable power, you can actually get rid of the eigenvalues that are the roots of unity. So it's a little bit in that span. Maybe I should say then that the unipotent part here would correspond actually to Dane twists along the curves that I've drawn. And now, Benson Farb's idea is that we should try to do something similar in higher dimension. Now, dimension 3 is rather boring because there is another theory of Thurston available, the geometrization of 3 manifolds. Decompose basically closed oriented 3 manifold into pieces, each with their own geometry, and such a diffeo will preserve that and act on each of these pieces with a finite order. Not so interesting. So it becomes interesting in dimension 4. And, well, this is virgin territory, so I think it's completely unexplored. So if you start out, you prefer things not to make too complicated. So assume that we have a simply connected core manifold, right? That simplifies things a lot. Then you have this most important invariant is then the second cohomology with its intersection pairing. And then among these, there of course the K3 stands out. All K3s are diffeomorphic to each other, so it's clear what I mean by say K3 manifold. Why does it stand out? Well, for lots of reasons, but one of them is that similar to the case of oriented surfaces of dimension 2, like these, which you have a kind of natural class of structures, metrics even, hyperbolic metrics. For K3s you have the Ricci flat metrics. And both have great moduli spaces. So in the first case you would get Teichmueller space, and in the other case you would get something that looks like an open subset of a cross-magnitude of positive free planes in this space. So that's in a nutshell the topic of my talk. So understand these. And well, how does it lead to the use of algebraic geometry? We're going to look at certain moduli spaces of K3 manifolds. So K3 manifold, certain structure. Well, we're quite used to that. If you have such a moduli space and you've really a family over it, you get, of course, a monodromy, also a geometric monodromy, and that geometric monodromy tends to preserve that structure. So that is something that's there to be exploited, and that's exactly what the plan is. So let me begin with recalling some facts from the late 1980s regarding the K3. So in this talk, M stands for K3 manifold, that is fixed. I orient M in the way we're used to, so that it has the intersection form as signature 319. Orient. Well, yeah, and so as I said, the most important invariant of a simple connected form manifold is H2, so let's do right away sort of agree that H will simply stand for the second integral cohomology with its intersection pairing, which we know is even unimodular. Right? And these properties, unimodular, these kind of signatures. Okay, well, that orientation is actually a topological invariant. So we have a representation of the group of homeomorphisms. So homeomorphisms are automatically then orientation preserving. No need to write a plus here. That has a representation on the orthogonal group of H. And of course that factors through the connected component group here. You could call this a topological mapping class group. It's a result of Quinn and Quinn. That's Benson 1996. That says that this is an isomorphism. if you replace homeo by diffeo, the things change a little bit. Let's first, the following result of Donaldson, proved 1 year later, shows the following. If we take the underlying real vector space, so this signature, we can consider in that vector space the space of, well, the plus stands for the positive definite three planes. This Grassmann is in fact a symmetric space for the real formable group. It's contractible in particular. And so if we take the topological bundle over the Grassmannian and restrict it to that open space, then certainly that bundle is going to be trivial. And now Donaldson tells us that this rank-free bundle is canonically oriented. In other words, every positive definite three-plane here comes with the natural orientation. Naturally oriented means here, among other things, that it is going to be invariant under the representation of the map of the diffeomorphism group. So if we take the diffeomorphism of M, of course also orientation preserving, then they preserve this other orientation as well. I will refer to this as a spinor orientation. And so we have a group, we have a map, like this. Same map as before, but that map will not land in, will land in a subgroup, namely the subgroup here, which preserves the spinor orientation. While this has 4 connected components, you can also introduce such an orientation for the orthogonal complement of this bundle. So, right, 4 choices here, and 2 of those connected components make up a group that I will denote like this. So this is respecting the spinor orientation. So it lands in here, and that was also observed then by Donaldson. And then I think the same year, basically, Borsia showed that this is actually onto. I should add that it is not known whether this map is, so this is what I, by the way, call mod of M, modular group of M. It's not known whether this map is injective. It could be something like a Torelli group, and that is the reason why I think most workers, well, most people who deal with K3 surfaces, prefer to have their K3s marked in homological terms rather than in sort of these diffeo terms. Okay. Now, in this kind of generality, there is a kind of Nielsen problem, Nielsen realization problem. Which was originally stated in this context of surfaces, and in this case, the context it was solved by Kirchhoff, by East. And it's the following. We have maps that I've just described. And suppose now I have here a subgroup, and the question is, it's a simple subgroup, be finite. And the question is, can I list this to, can I realize G as a group of symmetries of M? And the answer to that question can immediately be answered because it's no. And the example is familiar to most of you, I think, because if you have a very simple type of one parameter degeneration of K3 surfaces acquiring ordinary double point, then the monodromy there is given by the Picard-Lefschetz formula. So that's homologically a simple reflection. Well, let me write that. So H gives you the reflection here. And you can actually lift it to here. So that lifts as a Dane twist, a two-dimensional Dane twist, I should say. So that's the kind of monodromy transformation you get in the geometric situation that I just described. And that Dane twist has indeed the property that if you square it, it's isotropic to the identity. So you can lift it as a order 2 element in here, but you can never lift it as an order 2 element in here. You can never realize it as an involution, and you can actually easily deduce it from the Lefschetz fixed point formula. So that doesn't work. Benson and I sort of studied that question and determined, well, we were not complete in our discussion, but we could actually identify a lot of groups for which it's possible and for which it's and these finite groups. I want to focus here, so going back to this description that I gave here, of Thursdonian description of mapping classes. I want to focus actually on the class of mapping classes that are analogous to these Dane twists here, to the unipotent transformations. There will not appear as Dane twists there. This already shows it. It's quite a differentiation. But what we can say, at least, if I have a unipotent element in here, so, unipotent, that it will always preserve a primitive isotropic element, which is a primitive isotropic. Now, we know what these can represent for K3 manifolds, K3 surfaces in particular. It's the class, it represents an ample class, it's going to be close to representing genus 1 fibration or elliptic fibration, and that is indeed something that will appear in this slide. So let me first, before I proceed, let's fix a few things here. So if I take such an isotropic E, isotropic means of course E dot E is 0, simple, primitive means it's indivisible, particular non-zero, and then we can consider its formal part, so that is a degenerate sublattice, and the kernel of that sublattice is generated by E itself, so if I take the quotient, it is non-degenerate again. And it's even unimodular, of signature. I think it is 82. Okay. Perhaps it's also good at this point to mention the fact that if I have this spinor orientation, as I defined it here, every positive 3-plane comes with a canonical orientation, and you see right away that every positive definite 2-plane here comes with a canonical orientation. So this comes with a spinor orientation. So we can do the same thing as we did here. And I will write this simply by D of E. And as we know, if we orient these two planes, then we're basically dealing with a bounded symmetric domain of type 4. Is the one that classifies the type of Hodge structures that we have in hypercharacter. Okay, well, let me then introduce the first moduli space. Let me first of all emphasize that the moduli spaces that I'm going to consider are in general real analytic, not complex analytic, because I will insist, and that's appropriate in a place like this, that my moduli spaces are Hausdorff. So, we consider triples J, kappa, and E, given them, with J a complex structure, integral 1 of course. Kappa should be the class of a cohomology. So it's H R, right? Class of cohomology. And I normalize it. I wanted to have self-intersection 1. And then E is as before, it's primitive isotropic, but I require that this is in fact the class of a genus 1 fibration. With a complex structure that we've got here. Right? As you know, with E, there's at most associated at most one genus 1 fibration. I say genus 1 because it's not assumed that this has a section. Now, if I say moduli space, I really mean that I consider not just these triples, but basically the orbit of these orbit space with respect to the action of the diffeomorphism group. So I will simply denote that by M prim is the diff M orbit space of this. There are a couple of things to recall here. So we can consider, if we want to, for such a situation, for such a genus 1 fibration, so the genus 1 fibration, which matters here not the Taylor metric, we can look at automorphisms. Well, automorphisms with respect to complex structure that preserve every fiber and induce in every fiber a translation. That forms an abelian group. It's a well-known group. That's simply called the moduli group. So H. Translation in every fiber. Abelian group called the moduli group. Fine. Now, this is defined whether or not there exists a section, but if there is a section, then you can apply an element of the moduli group to it, and you get another one, and then in fact, all the sections are obtained in this manner. In other words, the sections form a torsor with respect to that group. So, if a section exists, then all of them make up a torso. Now, for reasons which will become clear in a moment, I want to focus, in fact, not on all such triples, but I want my genus 1 fibration to be such that all the fibers are integral. In other words, irreducible and reduced. And that, of course, limits these a bit. So let's say we apply integral if all fibers are. And the Kodaira classification of fibers then actually tells you that there can be only two types. They would nodes on the cusps. And that's it. This is Kodaira notation. Whether a vibration is integral can be read off from actually the hot structure of the KT manifold, because if you find an irreducible component of a fiber which is not the whole fiber, then it's basically a -2 vector. That -2 vector is perpendicular to the fiber class. It's of type 1,1, and in fact, the converse is also true. However, I do not know how I can read off from the hot structure whether there's a cuspidal fiber or not. Perhaps one of you knows how to do this. In case that's the case, then I'd like to hear it. Yeah, so this gives me a subspace. So we look at these triples, but now we insist that the pi that we find here is integral. So that gives me this. And I will denote it simply by well, there is for genus 1 vibration, there is an interesting standard construction, which is the formation of the Jacobian, which means that you replace every smooth fiber by its Jacobian, and you can do something similar for the pseudo fibers. And that produces, again, a vibration, but in this case, an elliptic vibration, because every fiber has now an origin. So that gives you a space that I will denote, mapping to a space, that I will denote like this. This is the formation of the Jacobian, so I call it J. It's a pretty drastic thing to do, so this is formation of the Jacobian. Because, well, first of all, the total space, so if I have this, if I have this genus 1 vibration and I take its Jacobian, then the total space is no longer M. It is diffeomorphic to M. But there's not a sort of privileged diffeomorphism or even an isotope in between these two. And what I also lose is, of course, the Kähler class. Here I had what was given a Kähler class, but that gets lost by this passage. On the other hand, if I'm dealing with a integral vibration, then this Jacobian vibration will also be integral. And then there's a canonical choice for even for a polarization. Because if you have this section, so you have this comes with a section, which I will denote by sigma 0. I allow myself to write E for the fiber class as well. Well, maybe I should not do that. Let's not do that. Let's call it 0. So then I can take 0 plus 3 times sigma 0. I hope I got that right. No, just the other way around. This is quick computation shows you that the self-intersection of this class is 4, and I want things normalized so that the self-intersection is 1. So let's divide by 2, and I get a canonical Taylor class. So that allows me to put this space back into here. I get a section. Now let's understand a little bit better what the situation is, what the relation is between these two. This Jacobian is formed by, well, let me say it like this. We have a filtration of H. Right? This is the orthogonal part of E, this is the E, and this is 0. This filtration is basically the Lorentz filtration for pi. So you see, so what we have here in the middle, that's the most important form. That is just and here you, I think here it is H0, 2, and here is H2, 0. And it's this subquotient that is used to produce the Jacobian. That's all you need. So in particular, we have more or less by construction that, maybe I should put here, see, that this sort of Lorentz subquotient for pi is the same as the Lorentz subquotient for this map. Oh, I used already my jelly, so let's call this Jack. We have this isomorphism, and yeah, the difference between the two is that here we have just this filtration, but for the Jacobian things are split. So the section sigma 0 splits the Lorentz filtration. And you can see that this is actually then, this becomes, I have to think about this, I think it is the class, I think it's sigma 0, and this is, well, this is already there. So that's the way you can propose. Okay, now let me then start stating the first theorem. Yeah, before I say it, I should observe that there is sort of rather boring map associated to this, but I think it's worthwhile to know that it's a map. And there's the following: we assign to a triple here simply the dot product of K and E. And so this maps to positive reals. So then the statement is that the map from this total space to the thing that I get from the Jacobian construction cross the positive reals that map actually is a rather pleasant map. It is like a torus over a torus. H tangent R. What do I mean by that? Well, over the general point, it is indeed a torus, but I have to be a little bit, sorry, the H is not the total space, it's H of P. So, right, so this is actually a torus, a real torus of dimension 20. I have to be careful with it because this is not quite true. And the reason is that, of course, this I divided out by so much. Also, a group that acts non-trivially here, so that this can only be locally true in a kind of orbifold sense. But I hope. So, like a torus, well, torus is not the word. Yeah, it's a torus, all right. But it's a torusor of a torus. So like a principal homogeneous space for this torus. That's part one of the theorem. Part two of the theorem is perhaps somewhat more familiar. It describes the space here. So this is the space. Via the Torelli theorem has a characterization of the local asymmetric variety. So remember that, I think it's still on the blackboard. Yes, there it is. I introduced this Grassmannia that I said it's a bounded symmetric domain. On that domain is, of course, acting the orthogonal orbit space. This, but I have to throw out something because I insisted. Wait a minute. I have to be careful with my. Yeah, sorry. I mixed up my notation. Yeah, doesn't let me correct myself. So. I wanted actually to consider here. Some spaces here. So this is also. And this is also what I meant here. Yeah, so I'm taking here those for which the fibers are integral. Without that assumption, I think that I could leave it like this, but I have to remove something. So we remove a divisor. It's actually a divisor that is geodesic. Metric that we have on the left, and it's irreducible. And the generic point represents a fibration, well, the simplest fibration that has a reducible codara fiber, and that's the following. Well, maybe I should go through the. Yeah, while I'm doing this is a good moment to ask questions if you have any.
What do you mean by like?
By what?
Like. It's like also?
Like, I mean. Without the like, it's not true. So it is like if you have if you take the universal orbifold cover of that, then it becomes that. But I have to mod out by something, and by modding it out, I also affect it acts non-trivially here. So it's like a local system.
That's not for your shoes.
Yeah.
So it's an R to the 20 torser over the orbifold.
Yes, yeah. Okay. I think if you use the right kind of terminology, then it's the lichen scratch.
So is M integral open in
Sorry?
is M integral open in M?
Yes, right. Yeah. Yeah, it's precisely because, well, I mean, that theorem sort of indicates that that is the case because I remove a divisor. And the Jacobian construction is compatible with integrality. Yeah, so the divisor, general generic point on the divisor. With an elliptic progression with a fiber like this. And this is of type 1, 2, 5. The form one family. Here it is.
But so the cuspidal ones are allowed, or?
Yes, these are allowed.
Yeah.
Yes. And I should say perhaps that this is this space here that appears in the literature. And I think people call it the Miranda moduli space. And it's orbifold fundamental group, because that's what will be of interest to us, was computed by Eduard Looijenga. For this computed, we found a presentation. I mean, it's satisfying that there is a presentation. I'm not so sure whether one can do anything with that presentation, but it's out there. Okay, now my second result, and this is, as I said, it's due to my collaborator, Benson Farb, himself. So the second result involves the orbifold fundamental groups that are involved here. So well, we have a Cartesian square. It's important to draw it in the right way.
Can I ask a question? So it's true this irreducible divisor is really codimension, real codimension 1.
Complex dimension 1.
Complex.
No. This sorry. This is, I would not use the word divisor in that case. So this is really a local and symmetric domain, right? A bounded symmetric domain modulo something, and you throw out something of complex dimension 1. So it's a honest device.
This is just the moduli of elliptic K3s without an I2 fiber, right? This is the mod, yeah.
Yeah, exactly. All right. Now, where default fundamental groups. So let's do this. All right. So we take the order for fundamental integral of this of the moduli space that I introduced, so the one over there. And the, well, we have, in a sort of strict sense, a family over it. But beware, this is all in the real analytic setting, right? This is not a complex structure. And we can look at the action on the middle dimensional homology, so the land in this group. But evidently, you are going to fix the element E. The land in here. And that's in fact true. We have also that going this way, so that's coming from the Jacobian construction, so that's there. And as you can see from this previous discussion, I think then it is really giving me, I don't want to have anything of interest, I'm just talking a bit of HE, also plus there. And there is of course an induced map like this. And the two maps that are drawn here are onto. Both come with sections. I actually described the section over there, so there's a section like this. You can also find a section here. That's given by this picture. What is a kernel of this? The kernel is initially identified with a letter, so I write it additively instead of multiplicatively. And that map is given by Eichler transformation. It goes like this. If you have an element in here, let's call it A, then the map itself by capital E. What is the Eichler transformation associated to A? It assigns to X the following. It's basically the exponential map, but it stops already rather quickly after the quadratic term. That's the way it looks. And that is this is a short exact sequence that has nothing to do with K3 surfaces, of course. This is something that works in lattices, and it's easy to verify. Well, this diagram here is Cartesian. And so the kernel of this map is the same as over there. So I can actually make it exactly like this. And both these maps are onto, so there's also a common kernel horizontally. Let's call that gamma. So I have now exact columns and exact rows. So or gamma is as follows. Okay, so this involves a little bit geometry here. So think of, well, I mean, these are moduli spaces of elliptic or genus 1 vibrations. So if you make in the base of such a base a loop, then looking what's happening over the loop, you come back to the original position. And of course, this is a kind of geometric monodromy that eventually will respect the fiber structure. So you get actually a self-map of M that preserves the vibration. It's only smoothly defined, of course, right? It is a monodromy, it's not something that respects the vibration. Now, if you have such a self-map, we have here this map. That's here, that's actually here as well. then, suppose we are in the most general situation where we have only nodal fibers, right? As you know, for a K3 manifold, if you have only nodal fibers, there are 24 of them. So there are 24 elements in P1 which move in that P1. Now, I'm cheating a little bit because this is not parameterized, it's just a genus zero curve with 24 points. So they move in it, but I sort of get a map, it seems, to the moduli space of this type. The moduli space has complex dimension 13, whereas the moduli space I'm involved with what did I say? Yeah, this moduli space has dimension 21. 21, and the moduli space that I get here has dimension 18, so there is actually you find here a sub-variety of codimension, complex codimension 3. You don't find it ever. But still, the kernel that I'm trying to describe is represented somehow as the mapping class grip of this. This is going to be a kind of spherical mapping class. Now, let me, in the time that remains, because I have to go quickly, say a little bit about how that group arises. So, it's given basically by simple loops around the divisor that I threw out. A general point of the divisor is represented by something like this. How do I make that sort of geometrically? So here, let's say, here we have our P1 with all these points, these 24 points. And suppose I have two of those points connected by an arc gamma with a property. So if I am on the interior of that arc, if I am on the interior of that arc, then moving to that point gives me a vanishing cycle. And moving to that point gives me a vanishing cycle. And in order to sort of ensure that if I shrink the arc, I end up with a picture like this, these two vanishing cycles better be the same. So in other words, if the fiber over this is given this genus 1 surface, then the vanishing cycle here, I could actually draw it like this, and the vanishing cycle there, I could draw it like this. These are, of course, isotopic, but it's clear that if I sort of contract them both, then I get this picture. And this is precisely the kind of thing that we must be dealing with. And so, how do you produce then the elements of this gamma? Well, you let you perform a gain twist over a regular neighborhood of the boundary of a regular neighborhood of such an arc, which basically means that you take these 2 points and you let one of the points just make a full circle around the other. And that definitely produces an element of this gamma. But there are other things you have to deal with, namely the Caspedal fibers. They are allowed, but they are responsible for the fact that the group gamma has also relations that you don't see right away. If I take now a gamma prime, and for which if I sort of do the shrinking and produce a cusp instead of this, so this should go to the cusp, then this picture is changed as follows. It is, you have a vanishing cycle like this and a vanishing cycle like that. And in that case, well, you know what the semi-universal deformation of a cusp is. It's a number, given by Weierstrass's normal form. So what you need to do in that case, instead of making one full circle, you have to make 3 full circles. That element is not only in gamma, but it is also killed in gamma. So gamma is basically characterized by these 2 properties. It's a way to define it as a subquotient of the spherical network. So that's something that I prefer not to write down, but I think it itself. Okay, now let us go back to what motivated this. So trying to understand mapping classes and represent them in a reasonable way. This story at least gives us a solution to one particular group, namely the group that appears here. We have this group here. This is a free abelian of rank 20, and it is mapped into there. And I am inclined to refer to this group as the differentiable Mordell-Weil group. Why? Well, we can consider in a situation like this all the diffeomorphisms that not only respect the fibers, but induce in every smooth fiber a translation, but now differentiable, right? Not no longer preserving the complex structure. That's an abelian group, right? So I can denote it like this. So the mod refers to the fact not that I have the identity component, but the fact that it's maybe this is the denotation. But I have to actually preserve every fiber and induce in every fiber something that is homotopically trivial, so a translation. This is this is a type of translation. We'll do a translation. That makes it surely commutative, right? This is an abelian group. Or in combination. So we can take the connected component group, and the connected component group will actually map to the image here. So it actually maps to and the observation is that this is an isomorphism, and that we have in fact a section like this, simply because this is commutative. You take a basis here, you choose a pre-image for every basis element, and then you get a subgroup that does the job. So we have here identified a subgroup of the stabilizer of E, which is completely realized as, well, for which you have the Nielsen realization. Okay, I think this is the moment to start.